Most people think artificial intelligence lives in software. They imagine algorithms running quietly somewhere in the cloud. But the cloud is not a cloud at all. It is physical infrastructure. Behind every AI response, image generation, search result, and recommendation is an enormous industrial system consuming electricity, water, computing hardware, communications infrastructure, and increasingly, advanced energy technologies. Companies like Meta, Microsoft, and OpenAI are not simply building software platforms. They are helping drive one of the largest infrastructure expansions of the modern era. Across the world, utilities are upgrading power grids, water systems are expanding capacity, fiber networks are multiplying, and new energy projects are being proposed to support the growing demands of artificial intelligence. This story is not really about AI. It is about civilization itself. It is about the hidden systems that power modern society and how those systems are being transformed to support a new digital age. Every AI model begins inside a data center. These facilities have become the factories of the digital age. Instead of producing steel, automobiles, or chemicals, they produce intelligence. Inside these buildings are thousands of servers connected through high-speed networks, operating continuously to train and run artificial intelligence systems. Data enters through fiber optic cables. Massive computing clusters process information at extraordinary speeds. Sophisticated networking equipment moves data between racks and systems. Operations centers monitor performance around the clock. What appears simple on a phone screen may actually require thousands of computers working together across multiple facilities. The scale is difficult to comprehend. Some modern AI campuses are comparable to industrial manufacturing complexes. The digital economy is increasingly dependent upon these facilities, making data centers one of the most important pieces of hidden infrastructure in modern civilization. Electricity is the lifeblood of artificial intelligence. Every server, network switch, cooling unit, and storage system depends on continuous power. The challenge is that AI is growing faster than many power systems were originally designed to support. Data centers now consume electricity on a scale once associated only with major industrial facilities. Utilities are upgrading substations, installing transformers, strengthening transmission corridors, and expanding grid infrastructure to meet rising demand. High-voltage power travels across long distances before entering substations where voltage levels are transformed and distributed safely to critical facilities. As AI expands, power reliability becomes increasingly important because even short interruptions can impact operations. This is creating new interest in energy resilience, backup power, and emerging technologies such as hydrogen-based energy storage and fuel cells. The future grid will likely look very different from today's grid because artificial intelligence is becoming one of its largest new customers. Behind every AI system is another resource that receives far less attention than electricity: water. Data centers generate enormous amounts of heat, and that heat must be removed continuously. Cooling systems rely on sophisticated water infrastructure that includes intake systems, treatment plants, purification equipment, cooling towers, heat exchangers, pumps, and recirculation networks. Water enters the system, is purified, used for cooling, and then treated before being returned safely. Advanced facilities operate closed-loop systems that maximize efficiency and reduce consumption. Without cooling, servers would quickly overheat and fail. This means water has become a critical part of the AI ecosystem. Interestingly, water is also essential for green hydrogen production through electrolysis. As AI and clean energy continue to grow, water infrastructure will become increasingly important because it supports both digital intelligence and future energy systems. As power demand continues growing, some organizations are looking beyond traditional utility connections. Dedicated energy systems are becoming increasingly attractive because they provide reliability, scalability, and energy security. AI campuses are exploring combinations of solar generation, battery storage, hydrogen systems, fuel cells, gas turbines, and even advanced nuclear technologies. The goal is simple: ensure continuous operation regardless of external conditions. Renewable energy provides clean electricity. Hydrogen offers long-duration storage. Fuel cells can provide clean backup power. Nuclear technologies offer stable baseload generation. Together, these technologies create diversified energy ecosystems capable of supporting massive digital infrastructure. Instead of depending entirely on distant power plants, future AI facilities may increasingly integrate energy generation directly into their campuses. This represents a significant shift in how infrastructure is designed and operated. When people think about AI, they usually focus on software. Yet software only exists because of an enormous collection of physical machines working together behind the scenes. Switchgear distributes electricity throughout the facility. UPS systems provide instant backup power during disturbances. Battery systems maintain critical operations. Chillers and cooling units remove heat. Pumps circulate water through cooling loops. Backup generators provide emergency power. Fuel systems store energy reserves. Control systems monitor every component continuously. These machines rarely appear in headlines, yet they are absolutely essential. If any of these systems fail, the entire facility becomes vulnerable. The hidden infrastructure behind AI is not a single machine, but a highly coordinated ecosystem of interconnected technologies designed to maintain reliability around the clock. Hydrogen is increasingly being viewed as a strategic technology within future digital infrastructure. The process begins with renewable electricity and purified water. Electrolyzers split water into hydrogen and oxygen. The hydrogen is then compressed, stored, transported, and ultimately converted back into electricity through fuel cells when needed. This creates a flexible energy storage system capable of supporting critical operations. Unlike conventional batteries, hydrogen can potentially provide energy for extended durations. Fuel cells produce electricity with water as their primary byproduct, making them attractive for low-emission backup power applications. For AI infrastructure that requires continuous operation, hydrogen offers an additional layer of resilience. While the technology continues to mature, many industry leaders see hydrogen playing an important role in future energy ecosystems. Hydrogen is not confined to data centers. It is becoming part of a much larger industrial ecosystem. Green hydrogen can support transportation, manufacturing, logistics, heavy industry, and power generation. Electrolyzer facilities convert renewable electricity into hydrogen. Storage systems preserve energy until needed. Pipelines and transport systems move hydrogen to end users. Fueling stations support vehicles and equipment. Fuel cells generate electricity for stationary and mobile applications. This interconnected network forms what many describe as the hydrogen economy. AI infrastructure represents just one potential application within a much broader system. The same technologies that support data centers may also support trucks, ships, industrial facilities, airports, and electrical grids. Understanding these connections helps reveal why hydrogen continues attracting significant attention across multiple industries. The future energy ecosystem is not likely to depend on a single technology. Instead, it will combine multiple systems working together. Renewable energy provides clean generation. Water infrastructure supports cooling and hydrogen production. Hydrogen offers storage and resilience. Smart grids connect everything together. AI systems optimize performance and efficiency. The result is an integrated infrastructure network designed to support both economic growth and sustainability goals. This convergence of technologies represents one of the most important infrastructure transformations currently underway. The boundaries between energy systems, water systems, communications networks, and digital technologies are becoming increasingly interconnected. Understanding these relationships helps explain how civilization evolves and adapts to new challenges. Hydrogen can be viewed as a bridge technology connecting today's infrastructure with tomorrow's energy needs. Renewable electricity powers electrolysis. Hydrogen stores energy for future use. Transportation systems distribute fuel where it is needed. Fuel cells convert hydrogen into electricity. Industrial users leverage hydrogen to reduce emissions. AI facilities may eventually use hydrogen to improve resilience and sustainability. The technology does not replace existing systems overnight. Instead, it integrates with current infrastructure while creating new opportunities for innovation. This makes hydrogen particularly interesting because it connects multiple sectors simultaneously. Energy, transportation, manufacturing, and digital infrastructure all intersect within the hydrogen value chain. When we step back and view the entire picture, we see that artificial intelligence is not simply a software revolution. It is an infrastructure revolution. Power systems generate electricity. Water systems enable cooling and hydrogen production. Electrolyzers convert electricity into hydrogen. Storage systems preserve energy. Fuel cells generate power when needed. Substations distribute electricity. Communications networks move data. Data centers transform information into intelligence. Every component contributes to a larger ecosystem. This is the hidden system behind modern civilization. It is a story of engineering, infrastructure, innovation, and interconnected technologies working together on an extraordinary scale. As AI continues expanding, understanding these hidden systems becomes increasingly important because the future of intelligence will ultimately depend on the infrastructure that supports it. The more we understand the systems behind civilization, the better prepared we become to build the next generation of energy, industry, and technology.